All right, folks, so we're back again talking about the Alpha 1500 watt power inverter. It converts DC 12 volt to AC 110. Has an AC outlet that does 1500 watts and a USB port that does 4.2 amps. What happened is I did a review of one of these about a week ago, and it pretty much was dead on arrival. It did not work correctly. And in my video, I said, hey, this thing's a piece of junk. And I returned it, and I got a full refund. I also got an email from the manufacturer of the inverter, and they were like, hey, we're really sorry about what happened. And they wanted to make it right. They were very, very nice, and they were very professional. And they offered to send me this replacement unit. I did not pay for this, so this is free of charge. If that upsets you and you have to click off the video, you can. But they sent this to me free of charge to do another review and see how this one goes. They were really concerned about my user experience, and they were very cool about the entire thing. Now, one thing is that when I was hooking this up to the battery that we were using for the testing, folks were saying that I did not give the capacitors an opportunity to charge or pre-charge in this device. So what I didn't show is off camera that I used a voltage tester, and I'll show you how we did that, to preload the capacitors here. In the emails back and forth between the manufacturer and I, they said that you could use a resistor, or that I should use a resistor to go in here and pre-charge those capacitors. Now, where that becomes a little bit of a problem is, let's say I've got this thing mounted in my camper, for example, and I use it, I turn it off, and the capacitors drain for whatever reason, and I go to turn it back on the next day. Maybe I have a kill switch between here and my battery or something like that. Then those capacitors are going to get that inrush of current, and it's going to cause that problem. The other thing is that, and I'm not saying it's going to cause a problem with this one, I'm saying it caused a problem with the last one. We haven't tested this one yet. And the other thing is that, and I'll give a zoom on this, these operating instructions here don't say anything about pre-charging your capacitors, or they don't say anything about using a resistor to slow the current as it comes in, or using a voltage tester, or anything like that. In this comprehensive user manual that we have here, it doesn't mention that at all. So if that's a requirement for this, it really should be part of the documentation, and perhaps a how-to instruction should be there. So let's just take a quick look at this so you folks can see what we're working with. I'm not sure how well that's going to come in. Here's our positive and negative poles. They seem to work pretty well. Dual fan. When I take a look at these poles, though, one of the things I'm going to note is they're large and they're robust, which I think is a good thing. But this is metal, which it should be, and it's recessed in this plastic, and it feels like it's like a hard plastic, like a Bakelite or something like that. You have to be careful not to over tighten these, because if you do, this could break, and then you would be stuck with this either on or off. The other thing, and I mentioned it last time around, is that a lot of times with inverters, you get some sort of dividing mechanism here. These are mounted a little bit further away from each other. In the event that your wires become loose and they twist and you don't have them properly heat shrinked, they could touch and they could cause some problems with that. Here on the other side, this is our voltage and amp indicator for what is coming out of the inverter. Here's our two 110 outlets or sockets here. This will tell you the voltage of the battery that you're using, or the system that you're using. On-off switch, and down here we have our USBs. These are both marked 2.1A, so when they say on the top of it 4.2 amps, I'm assuming that it's both of them together, and we'll test that out because we like to test those things out. And then down here is a light, and it's my understanding that if it's green, it means that the DC output is on. If it's off, it means the DC output, if it's red, the DC output is off. So not much to it, right? So that's just walking around. Let's get this thing set up in a place where we can, I'll show you how I pre-charged the capacitors. Again, in my opinion, perspective, that's probably something I shouldn't need to do because if this thing is mounted in a real world environment, that could be a problem for me. All right, let's get started. Okay, so hopefully this is going to make sense to everybody. On the inverter, I have two cables connected, positive and negative, and those cables terminate here at this set of Anderson power poles and then go into this fuse jumper that I made. This fuse jumper comes around, connects in here to another set of Anderson power poles, and then connects to this Ampere Time battery. The Ampere Time battery is a little one. It's a 12 amp battery. And I know that that's not enough to put 1500 watts through this inverter. In the email that I got from the manufacturer, they asked me to do the capacity test with the ampere time battery. And not the capacity test, I'm sorry, the capacitor preload. So I'm an agreeable guy, and I said yes. So what we do for this is we use this as a voltage tester, and it allows current to pass through at a slower rate than if it was just a direct connection. So we're going to go ahead and hook this alligator clip to the positive end of the battery. And then I'm going to come over here and I'm going to touch this. And you can see as the voltage goes through until the capacitors load, I get a little bit on my light here. Once this is out, the capacitors are loaded. It's exactly what I did before, and I should prohibit any inrush of current. Now, what I would want to do is directly connect this to my main battery that I'm going to use, and I shouldn't get that problem that we had the first time around. So we will go ahead and do the same procedure here with the bigger battery, but it all doesn't fit on camera, and so that's why I use this little battery, plus the vendor asked me to do that with this one. Hopefully that answers any questions. So in this test, what you can see, I'm connected here. Let me get this out of the way. I got the multimeter plugged in, and it says 10.7 volts, no amps because we're not really drawing any current. But this is 60.18 hertz, and that's about what you would expect to see in a situation like this. Let me go ahead and put this on here. 60.17. All right, let's just do a voltage measurement. And there we see 109.4 volts. And that's good. I mean, around 110 is I think is going to be sufficient here. Here we go, 109.5. So keep in mind, this is further than we got with the last inverter. So we're feeling pretty good about it right now. What I want to do is I want to do some tests on the USB socket. So let me get ready and we'll do that and be right back. Okay, so what we have here is the inverter powered up and we have the charge doctor plugged in. And you can see that it's pulling 1.49, 1.5 amps. We're charging the O1 oscilloscope. And it's doing it at 5.1 volts. And that's what you would expect from USB. Let me grab another device and we'll plug that in and charge that and see if there's any difference. So now we're charging this and you're seeing it go up to 1.5, 1.85. 1.86, and then here's our 5 volts. Let's get our load tester out, hook that up, and see what happens. Okay, here's our load tester, and let me go ahead and plug this into a power source, and it should come on. Oh, let me turn the power source on. All right, here you go, and you can see we are 5.1 volts, 0 amps. And so what I can do is I can start to turn this up to put a draw. So this is reading at 2.2, which is about what this says it can do for a single USB port. And here we're showing 2.7. Let's see if we can go up to 3. When we do that, we are seeing some voltage sag here. There we go. We're at 3 amps. I don't want to heat my cable up too much, but maybe we can go a little bit higher. 3.5. Now we're at 3 3/4. Just go all the way up to 4.2. So I'm a little surprised by that, to be honest with you. When it says 4.2 here, I'm assuming that it means across 2 ports. Let me see if I can find another charging cable and we'll charge something else. Okay, we're back. We're still pulling 4.2 out of here, and I'm just going to go ahead and plug my phone in. And now my phone's charging, and we're not seeing any drop here. So I'm impressed. Looks like we passed the USB test. Awesome stuff. All right, folks, just on a quick test here. So far, everything with this ALFFAA inverter is working out pretty well for us. I'm set up and I'm powered up, and I'm running off of actually a 200 amp hour Power Queen battery, which is a fantastic battery. So stay tuned for some videos on that. But here we have our O1 HDS oscilloscope connected, and I'll show you how it's connected afterwards. It's pretty precarious, so I don't want to show the connection with power running through it. But we're connected up, and we're coming out of this 110 outlet. This is reading 107 volts. And here's our sine wave. So this thing does generate a clean-ish sine wave. Actually looks very clean to me. What we're going to do next is we're going to bust this thing open and take a look inside. But let me turn that off, and then I'll go over the settings. So we have a 10x probe that comes out of the O1, goes down through these cords. Everybody's like, where? Let me see those cords. And it's just plugged into this janky cable that I threw together to do some testing. All right, folks, so we have the cover off, mainly because my buddy Ed said, hey, man, when you do the next video, I want to see the insides of that thing. So let's talk a little bit about it. Over on this side, you can see there's a add-on board here. I'm not 100% sure, but I believe that is the brains of the operation. So we're going to stay away from that. But here's where you have your input. Here's your terminals coming in from your power source or your battery. And then the positive you can see here is split into 3 different cables. Each one of these cables run over to these transformers. Now, a lot of times people will have these things open up and they'll be like, I want a big beefy transformer. What this is for DC to DC conversion. So when we have voltage coming in here, it's at 12, and when it comes out of here, it's got to be at 110. And so that's what is happening at this particular stage. And I believe all this gets filtered into, you can see some capacitors back here, but if you look down here, you can see some MOSFETs. There's 2 for each one of these. And then if you look, there's a little chip. There is what looks to be, I believe that is an inductor, but I'm not sure, and then a capacitor. And you have 3 sets, so that leads me to believe that this is all the input DC to DC conversion that takes place here. If I was to take this board out on the bottom, I believe there are some heavier traces that will get us over to this stage. And this is where, I guess it's rectification, for lack of a better word. But you see all of these little transistors along the back here. And the way that inverters work is that you have a DC loop of electricity, for lack of a better word, and you use a switching network, is what you would use these MOSFETs for, I believe, to reroute that energy different directions. And when you do that, you kind of get yourself a fake sine wave environment. All of that energy is going to come out through here. Everybody's like, oh, well, that's a toroidal transformer. It is a toroid, and it is wrapped up. But this is part of an LC network that you use in RF. So you think of AC. AC is a frequency, and you want to make sure that you keep that to a particular set of frequencies in order to maintain the integrity of your sine wave in a pure sine wave inverter. So what we have here is an inductor, and then down here are some capacitors. And I believe that this is just basically an LC filter that we use to keep the signal, the integrity of the sine wave. Here is what I would think is a choke. Then we're choking off our AC current as it comes out and goes out the plugs. Here you have some thinner wire that comes out of here and then goes into your display meters for your output. That's the extent of my knowledge of the innards of things like this inverter. I wanted to point out, so we have these fans also that blow air. These are your heat sinks, and you use those to keep these, basically these MOSFETs cool. And so air comes across these heat sinks and then out these grids in the back. That's the extent of my knowledge of the inside of this inverter. All right, now we are going to hook this up, and we're going to do some testing and pull some current through this and see how it performs. All right, folks, we have the inverter hooked up to the Unity UTP1306 DC power supply. And what we want to do is we want to test our cutoff voltage. Now here we have, let me move this camera back a little bit. We've got a green light, and this light will turn red when it turns off its output capability. Now at 10.5 volts coming out of the power supply, we should get a warning beep. And the inverter should cut off at 10 volts exactly. So let me go ahead and get started and see what we can get. So as we go down, we are at 10.7, 10.6, 10.5. And then there goes our warning beep. So it seems to be reasonably accurate. We also showing 10.5 on the inverter itself. Let's go down and drop to 10 and see what happens. Look at that. This is saying 10.1, 10 over here. We have the red light. We have the full-time beep. Now, I believe we got to go back up to around 12, 12 and a half to get this to re-engage. And there we go. We're re-engaging at 12.5. So it does what it says it's going to do. Next, we're going to put a load on this thing. We're going to do some load testing. All right, folks. So we have the inverter hooked up to the Power Queen 200 amp hour lithium ion battery. What we're going to do is we're going to fire this baby up, and there we go. Now, I'm going to use this tool. It is an output meter, and when I put it on here, it's going to cover up one of these two things. But it's going to give us data, so we're just going to go ahead and we're going to plug it in right here. And maybe I got to do some adjustments. Hopefully we can see that okay. That is showing watts right now. And for this load test, what we're going to do, let me grab it real quick, is we're going to use the Drill Master. And I don't know why heat gun's called a Drill Master, but it is. And it's from Harbor Freight. And this thing does 1500 watts, which is what the inverter is rated at. Now, this is an inductive load, I believe is what they call that, which means that it works well or requires sine wave to work better than a modified sine wave inverter. So we should be in business. So I've got this plugged in. I'm going to flip it on, and then we're going to see what happens. We also have this clamp meter down here showing us how much amperage is coming out of the battery. So right now it looks like it's 117, 116 amps. Over here, it's showing us 1,180 watts, give or take. This is the low setting. So I'd expect that to drop. There it is at 600. And then you can see on the clamp meter, we're at 58. Let's go back up. And it looks like we're at around 1181. When I look at the back, it's saying that we are pushing 10.5 amps out at 109 volts. So that's pretty good. I think that potentially, I keep bumping the camera, I'm sorry guys. I think that potentially we would maybe get more wattage out of this if our voltage was a little bit higher, but I'm really not going to complain. I feel, let me turn that off. I feel pretty okay with those test results. I'm not upset by them. And then you could see what our battery voltage was at there. But that's going to conclude that test. Let me wrap this up real quick. All right, folks. So we've done a number of tests with this thing. Remember, this is a replacement for one that I had that did not work well. And this one appears to work well. Now, what I didn't do is take it outside and hook it up to a bunch of industrial equipment and run it for hours and hours on end. I just did some cursory tests, and I feel pretty good with it. Would I buy this again at the sales price point of $199? I absolutely would. And I really want to say thanks to, I think this is ALFFAA, for making the situation right. Greatly appreciated, and I applaud the customer service from that company. That's really going to do it. If you have any questions, comments, suggestions, or recommendations, go ahead and post them below, and I'll do my best to respond. Thanks for watching, everybody.